So we're going to continue with question 5.23. The exhaust gases of a car are to be used to heat up water. 0.5 kilograms a second of hot gases enter the heat exchanger at a temperature of 250 degrees Celsius and leave at 150 degrees Celsius. If 0.5 kilograms per second of water enter the heat exchanger with an inlet temperature of 20 degrees Celsius, determine the temperature of the water at the exit. Assume Cp for the hot gases and for water is 1.08 and 4.186 kilojoules per kilogram Kelvin, respectively. So this is our first heat exchanger question. So what is a heat exchanger? A heat exchanger is basically just this box that two different flows will enter, and through some way, either by being placed near each other, or maybe one is sort of flowing annularly inside the other, you're just going to create sufficient contact that there's heat exchange between them, meaning the hotter one transfers heat to the colder one. And this is done a lot in many different cycles. You'll see, for example, condensers are heat exchangers. Really, you're just bringing hot gases in contact with the colder environment, right? And you'll see this a lot also in Thermo 2. Some ways you can make Brayton cycles more efficient is by adding heat exchangers. But the point is it's just a box where two fluid streams enter. One's hotter than the other, and they're allowed to transfer heat between them. So if we draw it out, here's our heat exchanger. Let's say we have fluid coming in here. We'll call this G in, which is the hot gases in. And of course, it eventually leaves G out, which is hot gases out. And sort of in the other direction, but it doesn't really matter which direction. If they're running in the same direction or against each other, the point is they're just near each other. We have water in, and then we have water out. And of course, inside the box, what's happening is you're passing these two, maybe they're pipes, you're passing them near each other, and they're allowed to transfer between themselves heat. So this might seem a little tricky at first, but it's actually pretty simple. And the reason it's simple is because we're going to use the first law of thermodynamics, and our system is going to be this entire thing. So we have four mass streams to deal with. We have one, the hot gas in, two, the now slightly colder gas out. Three, we have the the hot water out. And four, we have the cold water in, right? So the hot gas goes in with the cold water, and they're allowed to sort of, one's going to cool the other, one's going to heat the other. So the gas is going to get a little cooler, the water is going to get a little warmer. So the thing is, though, first let's start applying the first law of thermodynamics. So we know that Q dot minus W dot equals the change, well, since there's four different mass streams, it's going to take a long time to write it out. But basically, first law of thermodynamics is energy out minus energy in is Q dot minus W dot, right? And we'll look more specifically at what energy out and energy in is later. But the point is, what about Q and W? Is there heat exchange in this system? Is there heat exchange with a heat exchanger? Well, that depends on how you define the system. There's heat exchange, yes, between the two streams, but if you look at the heat exchanger as a whole, does the heat exchanger give away heat to its environment? No. All the heat that's being transferred is contained within this box, this black box. But the dashed box outlining the entire system, there's no heat transfer from that to the environment or vice versa. So this heat exchange is going to be zero. And work done, is there any work being done? No, there's no work being done in a heat exchanger. All we're doing is just letting things flow near each other. So there's no work being done. So again, we're left with this, I don't know why I did that, but 0 equals energy in minus energy out. So what's coming in? Well, anything that's pointing to the box is going into the box. So I can see 1 and 4, for example, are going in. So I'll say m dot 1 H1. So that's the mass flow rate of steam and at whatever enthalpy the hot gases come in at. Oh, sorry, I should be doing what goes out minus what goes in, excuse me. Not that it really makes a difference in this case, but just to be consistent. So m dot, what's going out? Mass streams 2 and 3 are going out. So mass stream 2 is the now slightly cooler gas. Mass stream 3 is the slightly warmer water. And minus all the energy that goes into the system. So m dot 1 H1, which is the hot gas, and m dot 4 H4, which is the cold water. Now, in this question, luckily, all the m dots are the same. It's 0.5 kilograms a second, so we can just cancel those. And we're left with 0 equals H2 plus H3 minus H1 minus H4. So what I'm going to do next is I'm going to bring all the H's referring to the same material on one side or the other. So I'm going to put the gases on the left side and the water on the right side. So H1 and H2 I'm going to bring over to the left. So it becomes H1 minus H2 equals H3 minus H4. All right, so we have gas on the left, water on the right. And we know by now for an ideal gas, we have Cp T1 minus T2. And this is, by the way, Cp for gas, which is different from Cp water. All right, so what do we know here? We're given the CPs, so those are known. We're told the inlet and exit temperature of the hot gas, so the entire left-hand side is known. And we're also given the inlet temperature of the water, so T4 is known. And that means we're just trying to solve T3, which is the exit temperature of the water. So if we substitute everything into here, we'll get don't know why it keeps doing that, 1.08 being CPG. Now, temperature 1, the inlet temperature of the gas is 250. It leaves at 150. And this is 4.18 times T3 minus T4. We don't know T3, but we know that T4 is 20. Now, I'm leaving it in Celsius because we're talking about a change. And of course, the Celsius and Kelvin scale are incremented the same way. So you could use Celsius in this case. But if you're ever unsure, just use Kelvin. In this case, though, it's okay. So anyways, we're solving here for T3. And we're getting 45.83. Sorry, 84 degrees Celsius is the exit temperature of the water.